Okay, so we were still on normal shocks. So let us do one more problem, and we'll sort of slowly move towards oblique shocks today. Okay. Okay, so let us look at this problem. So we have a point in a supersonic flow where the static pressure is 0.4 atmospheres. Okay, so let us say you consider right. So you consider a point in a supersonic flow where the static pressure .4 atmospheres, and then when a pitot tube is inserted, right, at this point we get a pressure of 3 atmospheres. So then we have a pitot tube which reads 3 atmospheres. We need to answer what is the Mach number, and secondly what is the okay. Okay, let's first answer this question. Okay, that what is the Mach number? Okay, so we have a supersonic flow, static pressure is this, pitot tube is this. So what is happening is that the pitot tube is actually reading the total pressure at this point. So what we can say essentially is that if you know, it's basically it's a supersonic wind tunnel, so it is going through a normal shock, right. So what we can see over here is that if I say this is say okay, this is 1 and this is say 2, right. So basically we have a flow coming in here. What we require is this, right. What we require is this, and what we know is right, and this is what is known to us. Okay, so this is the static reading at a particular point, and when we insert the pitot tube we get a reading for the total pressures which comes out to be 3 atmospheres. So what we can do from here is get this, right, and this is equal to say 7.5. Now again, if you go back to the tables, as we spoke in the last lecture, if you go back to the tables you will find a corresponding Mach number, right, corresponding Mach number which is 2.35. Okay, so therefore we have a supersonic flow, Mach number 2.35, you know, moving in a supersonic wind tunnel, which has, you know, pressures given like this. And so now, so therefore what we know now is that therefore we have this normal shock over here. Okay, so now in here, so what we would like to therefore calculate is the entropy change, right. Okay, so essentially what we see here is that there is a pressure change like this, and based on that we were able to calculate the incoming Mach number, right, from the tables. So now what we would like to see is what is the entropy change. Now from so this is the first, this is from the tables, right. Now from what we've done previously, so S2 minus S1 right. So this is something we derived in the last lecture, right. So the ratio of the total pressures after and before the shock, and this is known to us. Now how do we get this ratio? Well, we can get this ratio again from the tables corresponding to this Mach number. Okay, I'll leave you to do that. So just look up for Mach number 1, for M1 equal to 2.35, go look at the tables and find the corresponding ratio here, and that should give you the entropy change. Okay, with that we'll kind of put a little bit of, we'll take off from this normal shocks and look at a few things, and then probably even come back and connect to this one more time. Okay, so this is part of the problem. Now what we have done so far is we've connected the temperature changes, pressure changes, density changes, etc., as well as we've looked at total pressures, temperatures, densities, etc., across a shock wave in terms of the incoming Mach number, right? That's what we did right now. So we got these ratios, we calculated the corresponding Mach number, and we therefore got the corresponding entropy change. We did exactly that right now. Now what so therefore everything that we've done is in terms of the incoming velocity, the Mach number, etc. Okay, now what we could do one more time is basically connect all these properties just by themselves, in the sense that if there is a pressure change, what is the corresponding density change or specific volume change, etc., without any reference to this Mach number at all. Okay, so let us see if we can do that. Okay, now if we go back, so we have our continuity equation, right? And so right. So this is from the continuity, right? This is from continuity, and okay. So then from here, so let's say call this as 1. Okay. Now, so what we will do here is we will write okay. So we will write this from the continuity. Now again from the momentum equation, which is okay. So what we will do is basically, okay, let's say this relationship is right. So what we will do is we will incorporate this relationship here. Okay, we'll incorporate this into this. So in this equation 2, what we will do is we will replace this u2 by this. Okay, so which makes this equation therefore u2 is u1 this is what we get. So you can see that we do not have any u2 term over here, right? And then we will solve for u1. Okay, and what we get is this. We'll solve for u1. So what we get is this. Okay, so we get this, and say let's call this as A. Okay, so we get an expression for u1 in terms of just the pressures and densities, right? Okay, now we'll do a similar thing for we'll solve similarly for u2. Okay, if we do that, so basically for that what we will do is we will write this equation in terms of u1. So we can also write this as right, this is u1, and then into this equation we will replace u1 square by this expression, right, by this expression, and what we will come up with is then we will solve for u2, and what we get for u2 is this. Okay. Right, so this is what we get for u1 and u2 square. Now, what we will do now is let us go to the energy equation, right. Now, energy equation right. Now, here, so we basically have, now I hope you can kind of see where I am getting at. So, we have this u1 square term and u2 square term. So, we have velocity terms there, and what we can do if we use these two expressions for u1 square and u2 square is totally get rid of any velocity term and just replace it in terms of just the variables, just the thermodynamic variables here, right. So, we have pressures and densities. So, we can actually do that there. Okay. What about the enthalpy? Can we write that in any other way? For example, H, as you know, is right. So, therefore, if I use all of that, if I replace this by all the H1 and H2 by an expression for enthalpy, and we incorporate A and B, what we end up is something like this. Okay, or okay. So, what we get over here is a set of these expressions. So, all we have done is worked with the continuity, the momentum and the energy equations, just simple playing around with the properties, and all we did was we took away any sort of reference to velocities, okay, and we were able to generate this equation with just the thermodynamic variables. Okay. So, we have the specific energy change in terms of the pressures and specific volumes and corresponding, you can also write this in terms of densities. Now, these two basically forms are known as so basically the Rankine-Hunio's equation. Okay. So, these two, and as you can see, like kind of repeating this, that basically this has an advantage because there is really no reference to the Mach numbers or velocities, and it is specifically relationship just between the thermodynamic variables. Also, we do not have any specific reference to a gas in terms of we do not have a gamma over here, right. So, it is independent. So, this is valid for any sort of fluid. Okay. Now, having said that, let us see if we can use this a little bit in little bit more. So, in order to do that, let us say basically if we can use that more functionally. So, if I have to do that, so let us do this. Okay. So, we have okay, let us look at this. So, if now we know these, right. see if we can sort of use this in any way. Okay. Now, CV again can be written as okay, and from here right. So, what we can write E as is right. Now, if I do that and then incorporate this relationship, right, if I incorporate this relationship into the Rankine-Hunio's equation, we will get something like this. Okay. Right. And we can also of course write this as yeah. Okay. So, this is okay. So, what we have done is first we wrote out our basic equations of flow governing a normal shock. Okay. Then we got rid of any velocity terms using the 3 basic governing equations, and we came up with the Rankine-Hunio's equations. Now, in the Rankine-Hunio's equation, we did some more manipulations and we came up with this sort of a relationship. Now, what this is a very interesting relationship, because if you see what this is telling us is the way the specific volumes with a particular value of specific volume change, the pressure will change. With this particular range of density changes, how the pressure will change. So, essentially if I were to plot this right for various values of V1 by V2 or rho 2 by rho 1, then I will basically get a curve which is telling me how the corresponding pressures are changing. Okay. Now this is this basic expression is called the Rankine-Hunio's relationship, and I would suggest you that you go and look in any standard book. So, you will get the Rankine-Hunio's curve. Okay. And it will look it's interesting to see. So, right. So, if you will get curves like that, and say for say corresponding say right, you will get curves like this, and what it will show is how that differs from the isentropic relationship, in the sense that you will have an isentropic curve, right. Now, this is an isentropic curve, right, whereas this is the curve which is resulting from this relationship, and this is telling us the difference. This is basically telling us the difference for across a relations between across a normal shock. Okay. So, this is something you can look up in any standard book. This is available, and just sort of get familiarized with it. Okay. Now, so that kind of more or less takes care of what I wanted to talk about, normal shocks, etc. Now, the next thing to do immediately is oblique shocks. Okay. Now, at the outset, let me just say that normal shocks are a special case of oblique shocks. Okay. We will see what that means. Okay. So far what we have done is that, say we have a normal shock like that, we have flow coming in. So we calculate velocities, we calculate basically the properties at in regions behind in front and behind the shock. Now so therefore this is like a normal shock. Now what happens if there is an oblique shock? Okay, so we'll look at some pictures of oblique shocks, but I think we did that in some of the earlier classes. So let us see what we are looking at and see if how basically our properties will change across an oblique shock, and if it is how different it is, if at all, from the normal shock relationships that we have developed so far. Okay, so let us get some geometry in place. Okay, now say this is basically an oblique shock, right? Again, so this is basically a very thin region across which there is a large gradient of the flow properties. Okay, so what we have seen in the corresponding normal shock is this is the small region across which properties are changing, right? In now what we will consider is this is not perpendicular, but this is inclined to the horizontal at some angle say beta. Okay, now what we will say here is, so therefore here too, so we have an incoming velocity like that, right? And let us say that when it hits the oblique shock here, okay, it moves with V2 and so the angle that it makes with the horizontal is theta. Okay, so angle of the shock is beta, and angle of the this velocity vector behind the shock is theta. Okay, if we do this, now we'll do a couple of things over here. So now my corresponding say Mach number here is m1 and my corresponding Mach number is m2. Okay, now let us do a couple of things over here. Now let us do this. Okay, I probably need to do this at the bottom. Okay, now we'll take the same shock here. Okay, on this shock let us take basically what I want to do is, right, this is my now what I will do is consider a, so this is my V1 and this is V2, right? This is V2. Okay, now let us do this over here. Now what we will do is we will draw a control volume like this. Okay. Okay, now if I need to get this right. Okay, now this okay, so therefore this is essentially V2. Now if I take this over here, so if I call this A, or let us say this side is A, B, C, D, E, and F. Okay. Now, what we will do is essentially so this is my control volume. Okay. So, now this F and C, these are parallel to this parallel to the oblique shock. So, these sides, the sides here, okay. Okay, so let's sort of, this helps me do this. Let's call it this. Okay. Now let's say this is A, B, C, D, E, and F. Okay. So now here, this A and D, these are parallel to the shock. Okay, I hope I have drawn it right. So, basically A and D, these sides are parallel to the shock, and let us say the corresponding areas are A1 and A2. So, you can see that these are actually equal here. Okay. So, now what and then as we know that this is essentially the velocity vector, right. This is the incoming velocity vector. Okay. Now, what we will do here is, if I do this over here, that I will draw components of this velocity vector v1, okay, like this. One is, this is a velocity vector which we will call as u1, okay, and the other one okay, u1 and w1, okay, and the corresponding, say, Mach number here is, right, because the reason we write n here is because this is normal to the shock, okay, and the w1 here is, it is tangential, so we call this as this. Okay. So, similarly on the right hand side we will do the same thing. So, we will drop a perpendicular, and this is my u2 and the corresponding and 2, right, and right. So, okay, this is u2 and this is w2 and mt2. Okay. So, this is essentially the geometry over here. Okay, and I am drawing this separately just to give some clarity. So, all I am doing is drawing a drawing up a control volume which is encompassing this, okay, which is encompassing this. So, I have this velocity vector over here and I draw a control volume so that I can apply the integral forms of the governing equations to this to it. Okay. So, what I have done here, now the question is why did we do this? Now, you will see the usefulness of this in a bit, I hope, is if you just look at this part, this u1 here, this is just like a normal shock, isn't it? So, what we had earlier, right, what we had earlier was the shock was like this, right, and you had a velocity vector coming in this way, right, say v1 and v2. Okay. Now, just think of this, just take this and rotate it in this way. Okay. So, say I rotate this, okay. So, let us say I rotate this whole thing. Right. So, this is the normal shock. Okay. So, say I call this as A. So, therefore, this is say A dash. Okay, I have just rotated that. Therefore, this velocity component, how does that change? Now, that becomes, that is also rotating this way, right. So, then this is my say V1 dash or and V2 dash. Now, if you compare this, that is exactly what I have done over here. Okay. So, this is my shock now, this is my shock now. So, therefore, the corresponding velocity component is normal. So, one component is normal and the other is tangential to it. Okay. And we will see the usefulness of this, and if at all this will have any special implications on the properties across an oblique shock. Okay. We will see that. This was just to bring the sort of relevance to the normal shock. Okay. So, now if we do that, what we will do simply is what we have done before, apply the equations, governing equations to this normal shock, to this oblique shock. Okay. Now, what we will use is the steady form of the integral form of the governing equations, right. So, I am not going to write out the entire equation. So, for example, okay, let me write this because this is small. Okay. So, continuity is essentially okay. So, we will consider the, so this is basically the integral form of the equation. Now, we can, so we will consider the steady form of the equation. So, what we get is this, right. Now, what we have seen, what if you recall what we did in the earlier case. Now, so essentially we have the velocities, this is the V1 impinging on this face and this is my total control volume. Right. Now, if you consider this in this case V dot ds. So, areas, like I said, areas is A1 and A2. So, I will just write it for this face and this, all these faces, and see what we get, right. So, we have two components, one is U1 and one is W1. U1 is perpendicular to the face and W1 is parallel to the face, okay, to the shock here. So, if I have so basically I have this, okay. So, this is my U1, okay, and if you remember correctly, my area vector is essentially this, right. This is my area vector. So, therefore, if I had to write this integral for this component of the velocity, so what we will get here is right. And similarly, now for the normal component, so for the normal component is this, right. So, this is the W1. So, this does not contribute anything over here, okay, because these two are perpendicular. So, okay. So, dot product does not give us anything. So, in that case we get this, and on the outside again if we do this, right. So, here essentially, so we have this, right, we have another perpendicular, okay, and this is the U2, okay, and again this is the A2, okay, if you remember correctly. So, what you have to notice essentially is that the area vector and u1 vector are opposite to each other. Here they are in the same directions, okay. That is what just brings in the sign over here, okay, because the angle between u1 and a1 is pi, isn't it, and the angle between u2 and a2 is 0, okay. So, that is the reason we get this. So, plus rho 2 u2 a2 is equal to 0. So, that is what we get, and what we have to notice here is that again here. So, then this is the parallel component, and this again the angle between this and A2 is 90. So, therefore, that does not contribute to the integral over here, okay. So, what we get from here. So, therefore, in here we know that sorry. So, A1 is equal to A2, right. So, so therefore, what we get from here is so this is what we get from the continuity equation, okay. Rho 1 u1 is equal to rho 2 e2. Now, how is this different from the normal shock? It is not, isn't it? But what you should notice over here is that u1 and u2 are the normal components of the velocity, which is impinging at the oblique shock, okay. So, what this is similar to the continuity equation, if you apply it for an oblique shock, is same as the normal shock, provided we take the normal component of the velocity, okay. So, what we wrote there is not rho 1 v1, instead what we wrote was rho 1 u1, okay. So, that is important to notice here. So, what we are using over here is the normal component of the velocity across the oblique shock, okay, and then this is the relationship we get from there, okay. So, now having done continuity, let us go ahead and see what we can do with the momentum equation, like we have done earlier. Okay. So, all right. So, I am not going to write out the entire momentum equation. So, for steady case, okay, for steady case, this is what we have done before, right. So, now we will apply the same thing to the control volume that we have derived over here, okay. So, now if I do that, what I shall get is this, okay. So, again okay, let us do this. So, therefore, here now this V, now what this can be here is, so basically we have again two components, right. So, we have U and W, isn't it. So, what, let us do this over here, okay. Now, so basically we have two components. Okay, and okay, and then this. So, for the right hand side, what we get is well, clearly we do not have a pressure component parallel to the shock. I think that we know, right. Okay, now if we do this, okay, now if we do this, let us just take okay, before we do that. So, A1 is equal to A2, right, that we know so far. So, that sort of that A, all the area terms sort of disappear from here. Okay. Now, let us take the parallel component first, okay, that is W1. Let us take that from here and see what we get. Okay. So, what we get is this rho 1 U1 W1 plus rho 2 U2 W2, right, because from here the pressure, there is no component in the parallel direction. There is no component of the pressure in this direction. The pressure is only acting normal to the oblique shock, right. So, if that is so, when I take this velocity as W1, I get this, isn't it. So, there is no pressure term in this direction. Now, if I do that, now what we have, so essentially what we have seen here is that rho 1 U1 W1 is equal to rho 2 U2 W2. So, this is what we get, right. This is what we get if we are looking in the parallel direction. So, this is the parallel to the oblique shock, parallel to the oblique shock. Right. Now, if I do this, right, if I do this, now from the continuity we have just obtained that rho 1 U1 is equal to rho 2 U2, isn't it? We have just obtained it. If you look here, so rho 1 U1 is equal to rho 2 U2. So, these two are same, which means that W1 is equal to W2. Now, this is a very interesting result for an oblique shock, that in an oblique shock there is no change in the parallel component, right. So, although the U1 is changing, right, the U1 is changing, there is no change in the parallel component. So, the change in the velocity is actually, so we basically have an impinging velocity of V1 which becomes V2, but this V2 is because of the change in the normal component and there is no change whatsoever in the parallel component. So, for an oblique shock, W1 is equal to W2, and that is a very interesting result. Okay. So, this is what we get from the momentum equation. So, let us just sort of complete this and use the energy equation. Okay. Okay, before we do that, so we use the parallel component. Let us also do the normal component and see what we get, right. So, if I do the normal component, then what we get is right, or yeah, okay. So, if we work up with this, what we get is okay. Now, I think that we missed a over here, right, this, right. Okay. So, if we get this, so then we get this this relationship, which is exactly the same as for a normal shock, right. This is exactly the same as that, and again you can see that what we are using here is the normal component of the velocity across the oblique shock. Okay. So, therefore, what we got from continuity and from momentum with the normal component of the velocity is the same as that we got for a normal shock. Okay. So, let us complete this and write out the energy equation. Now, the energy equation, again it is I am going to not write the whole equation. What I will write is for the steady case, right, for the steady state case. Right. So, this is right, this is equal to so this is my energy equation. Okay. This is my energy equation, and what we shall do over here is that here, so basically we will put V1, right. So, this will be V1 and V2, right, across the right, and again we will do, write out this equation. Now, if we write this out, right, if I say write this out, so what we shall get, okay, without sort of writing out the details of this, what we get is this. Right, but rho 1 U 1 is equal to rho 2 U 2. Therefore, what we get is right. Now, here of course, what you can see is that we are actually using the total velocities, because we are not using any component, we are actually using the total velocity before and after the shock. Now, V 1 square of course is equal to this, right, and V 2 square is also equal to, right. Okay. But what we have seen now is that W 1 is equal to W 2, right. So, therefore, I can actually write this, I can write this equation. So, this equation as, so this okay, so it becomes right, but W 1 is equal to W 2, we have just shown that. So, which means that we can sort of, or you can cancel it out on either side. So, then what we get for the energy equation is okay. So, finally, so what we see is that if we are going to say, let's kind of summarize this, right. If I had to summarize this, okay, this is my continuity, this is my momentum, and this. Okay. So, this is my continuity, this is my momentum, and this is my energy equation, which is exact for an oblique shock. And what we see here is that we are using the normal component of the velocity before and after of the shock, and these relations are exactly the same as we had derived for a normal shock. Okay. And what we notice from here, one more inference that we got from here was that W1 is equal to W2, which is that the normal component of the parallel component of the velocity does not change across the oblique shock. Okay. So, therefore, we basically that is the connection with the normal shocks, and therefore, what we can do here is we can use the same tables that we used for normal shock, right. For the only thing will be that we will use the normal component of the velocity, right, and the corresponding Mach numbers. So, we will see how we will do that in the next few classes. So, that should be all. Thank you.